The Taylor polynomial for functions of two variables, that's what we're going to write now. And there's going to be something neat going on. And the neat thing is that I'm going to remind you of the Taylor polynomial for single variable. And we're actually going to prove, we're going to develop the Taylor polynomial for two variables from the single variable version. Okay? Usually the Taylor theorem in Calc 1, the full theorem is usually not proved because it's not a simple proof. It's a rather complicated proof which relies on a theorem called Cauchy's theorem, which is usually not even in the material of Calc 1. So, but here we're going to generalize the Calc 1 polynomial to the Calc 2 polynomial, and you're going to see the resemblance. The ideas are very, very similar. So let's start by a reminder. Now, since our function in two variables is going to be called f of xy, x is taken, y is taken, and f is taken. Okay? So the function in one variable, for the reminder, and the one we're going to use, is going to be called g, and the variable is going to be called t. Think you can live with this? Good. Okay. So what is the Taylor polynomial? I'm actually going to write what we call the Maclaurin polynomial, the Taylor polynomial around the point 0. Okay. So what is it? It's the value of g at 0 plus the derivative of g at 0 divided by 1 factorial times t, or t minus 0, right? Plus the second derivative of g at the point 0 divided by 2 factorial times t squared, right? Remember this? Does it bring back memories? Good memories, I hope. Okay. Plus, and however far we go, the nth derivative at 0 divided by n factorial times t to the n. Let's write this 0 down here. Right? This is the Taylor polynomial of degree n evaluated around 0 for the function g. Right? Now there's one thing wrong on the board right now. This equal sign. The function does not equal its Taylor polynomial. Right, it's about the same as the Taylor polynomial. And there's a whole discussion of what this about means. I'm not going to review it. But it does equal when we add what we call the remainder. Rn, let's just call it. Right? Then it equals. And one can write the remainder in various forms. You probably discussed the Lagrange form of the remainder, and then you can, based on estimates of how bad the remainder is, how big it is, you can approximate things using the Taylor polynomial up to a given error, which is the remainder, right? That's the broad concept of what do we do with the Taylor polynomial, right? Everybody with me? Okay. So, now what we want to do, now, take a function in two variables, fx, y, and we will develop the corresponding Taylor polynomial around 0, 0. Okay, and afterwards I'll tell you how to write it for a general point AB. Okay, there's nothing special about 0. It just makes all the calculations more easy to see. Not easy to calculate, easy to see. Okay, so here's the idea. A function of two variables. What I'm looking at is a bird's eye view of the domain. Okay, so this is the x-axis. This is the y-axis. This is the point 0, 0. Where is the graph? right? Everybody know what I'm doing? Exactly. The graph is up here of fxy. Good? Okay. Now I want to find, let's look at a point here, call it AB. I want to find the Taylor polynomial for the function at a given point xy near 0, 0, and along, what I'm going to do is use points along the line connecting 0, 0 at AB. I'll explain in a minute. So here's the idea. I'm going to connect the given point AB with 0, 0 with a straight line. And I'm going to parameterize this line. A very trivial parameterization for this line is, so any point along this line is of the form TA, TB, where t ranges between 0 and 1. Do you agree? When t is 0, you get the point 0, 0. When t is 1, you get the point AB. And any point along this line is of this form. Do you agree? Good? Okay. Now, I'm going to define a new function. We're going to call it g. It's going to be a function of a single variable t. And the way I'm going to define it is as a composition. We've done things like this before. I'm going to take f, which is a two-variable function, and evaluate it at points along this line, at ta, tb. That's the value of g at t. Okay, so namely, if f lives up here, this is the curve gamma, whose parametrization is this, and I'm only looking at values of f on points on this curve. Do you agree? F at points like this, f at points like this, and I'm calling it g of t. Do you agree? We've discussed things like this several times. We discussed it when we mentioned the chain rule. We discussed it when we did the intermediate value theorem. Remember? We looked at values of functions along curves. This is a simple curve, but we did it on more complicated curves. Okay. And again, I'll mention here that t ranges between 0 and 1. Okay. Now, I want to use our Taylor polynomial for the function g of a single variable and see what it gives in terms of f. Okay? And by very simple arguments, we're going to be able to somehow reveal out of that the Taylor polynomial for f itself. Okay, let's do that. So let's peek just for 1 second at this board. This is the Taylor polynomial for g, right? I want to evaluate all these things I need in order to find the polynomial. I want to write what g of 0 is, what g prime of 0 is, what g prime prime of 0 is. All these I'm going to calculate, plug them in, and they're going to be given in terms of f, because g is given in terms of f. Do you agree? Okay, let's see that. So, what is g of 0? Let's write up here that g of t, in general, was, by definition, f of a, or I wrote it, ta, tb. That's the definition of g. So what is g of 0? You have to plug in 0 here. You get f at 0, 0. Do you agree? What is g prime of t in general? What is the derivative of g with respect to t? How do I find it? I have to use the chain rule on this. Do you agree? So I have to take the derivative of f with respect to its first variable, f sub x, evaluate at the point ta, right? Times the inner derivative. What's the derivative of this thing with respect to t? A. Right? Plus the derivative of f with respect to its second variable, whatever that is, f sub y, evaluate at that point, times the derivative of this with respect to t, b. Does everybody agree? Good? And what we need is g prime at 0. So what is g prime at 0? It's the derivative of f with respect to x evaluated at 0. Ah, I made a mistake here. Where should I evaluate it? Right. This is a two-variable function, right? Let's fix this. ta tb times a plus fy at ta tb times b. Good? Is it clear what just happened? Why I got confused and why this is the correct thing to write?
When you say f at x, does that just mean the first variable?
This is the same as this, and it's the same as df to dx.
No, but is the dx the ta?
The x is the first variable of f. Okay? F is a function of two variables, x and y.
Okay.
Right? Chain rule, take f with respect to its first variable, then take the inner derivative, a. Good? Okay, so what do I get? G prime at 0 is f, the derivative of f with respect to x, at plug in t equals 0, so you get 0, 0, times a, plus fy at 0, 0, times b. Does everybody agree? Good? This is g prime at 0. Let's move on. What is g prime prime at t? What is the second derivative of g with respect to t? So what do I have to take the derivative of in order to find it? I have to take the derivative of g prime of t, right? And then evaluate it at 0. So let's do it. What's the derivative of this thing? It's the derivative of fx with respect to its first variable. Let's not write the ta, tb all along, because it just gets too fat. So I'm going to write fx, that's the derivative of this with respect to its first variable, times the inner derivative, a, plus the derivative of fx with respect to its second derivative, which we denoted fxy, times the inner derivative here, b, and all of this times this a. Everybody with me? Plus, now I'm doing the same here. I'm taking the derivative of fy with respect to its first coordinate, to x, times the inner derivative, a, plus the derivative of fy with respect to its second variable, y again, times its inner derivative, b, and all of this times the b out here. Do you agree? Good? And now, remember the theorem that we had about the equality of the mixed partials. Okay? In order to do Taylor in general, we're going to need to assume that the function has nth order partial derivatives, right? So in particular, all the ones in between have to be continuous because they're even differentiable because they exist, right? So the partials are equal. So fyx and fxy are the same, right? So I can rewrite this as a squared times fxx plus ab times fxy plus ab times fyx, but they're equal. So plus 2ab fxy plus b squared times fyy. Do you agree? Everybody? And in particular, evaluated at 0, g prime prime at 0 is a squared fxx evaluated at 0 plus 2ab fxy evaluated at 0. Make sure there's clear distinction in what you write between these subscripts, which denote the partials, and variables, which sit in parentheses, okay? that you don't start writing things with x's and y's floating in various heights, you can get very confused. Plus b squared fyy evaluated at 0. Is this clear? Okay. Now you can go on. You can find g prime 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 of t. How do you do this? You take the derivative of this, right? With respect to t. So you use a chain rule. You find the derivative of, remember that fxx at tatb, right? So you again, it gets repetitive, right? And you will find, if you haven't guessed already, can somebody guess what, looking at this, what does this remind you of? Exactly, right? It kind of looks like the binomial coefficients. Do you see that? That's the kind of behavior that it shows. So what do you expect g prime 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 of t to be? Right, slowly, so I can write a cubed fxxx plus, exactly, 3a squared b fxxy. Does the order matter? If I write xyx or xxy or yxx, it doesn't matter, right? Because mixed partials are equal. Okay, plus, exactly. And finally, b cubed fyy. And at 0, you just plug in zeros. Good? Clear? Okay. And you can go on and you can prove by induction, if you want to do it completely rigorously, that indeed the nth derivative of g with respect to t is given by this sort of binomial expression where the binomialness is in the coefficients, but also in the variables with respect to which you take the partials. Okay? So now let's see what we can learn from this. So, let me rewrite, let's summarize everything and write the following. G of t, remember g of t was g of 0, but g of 0 we found was f at 0, 0, right? Plus g prime at 0 divided by 1 factorial times t. But g prime at 0 we found was a fx at 0, 0 plus b fy at 0, 0 divided by 1 factorial times t, right? Plus g prime prime at 0, which we found equals a squared fxx at 0, 0 plus 2ab fxy at 0, 0 plus b squared fyy at 0, 0. All of this times t squared over 2 factorial, right? I'm just plugging in what we found for the derivatives of g with respect to t in the previous board. Good? Everybody with me? Everybody? Wonderful. Plus, and let me add dot, dot, dot. You can go as far as you want. But let's recall several things. So the first thing I want to recall is, remember how we defined g of t. G of t was f at tatb. Okay? So if I look at a point, so what I want to say is ta was x, was the x coordinate of a point. Okay? And tb was y, was the y coordinate of the point. And g of t was f at tatb, so it's f at xy. Clear? So I can plug in all these, and what do I get? Well, Instead of g of t, I'm going to write f of xy equals, and this is this f of xy. So these are the explanations for this. And I'm going to replace all of these. So it's f at 0, 0 plus. Note that here I have a times t. What is a times t? X. So I have x times fx at 0, 0. bt is y plus y times fy at 0, 0. So this is the first order expression. Plus, what do I get from this? I get 1 over 2 factorial, that's this. A squared t squared is x squared. So I get x squared fxx at 0, 0 plus 2abt squared is 2xy. 2xy fxy at 0, 0 plus b squared t squared is y squared. Y squared fyy at 0, 0 plus dot, dot, dot. Clear? Good? So, and note that what we got here is no longer dependent on what A was, what B was, what G was. It's a statement only about F. Do you see that? Okay. So this is called the Taylor polynomial. In this case of degree 2, and depending on how far you go, of degree n, corresponding to F at the point xy evaluated around 0, 0. Clear? Okay. Let's go back for a second to this board. So what happened here? I wanted to evaluate the polynomial near 0, 0 at some point xy, this point. Okay. So I parameterize the line crossing through this point, going up to whatever point I want. Okay. And that's what I use. So everything in our discussion was auxiliary, just in order to be able to use the Taylor polynomial in single variable. Okay, so this was the point I was interested in, xy, and I found that f at the point xy was precisely that expression. Okay, so let's add here, there's a plus dot dot dot, plus there's going to be some remainder. Let's write some remainder. For the purpose of this course, we will not need formulas, explicit formulas for the remainder, and we're not going to go through more subtle discussions of behavior of the remainder and how to evaluate things using it. The idea is completely analogous to Calc 1, completely analogous. And we are going to use the Taylor polynomial, and usually up to degree 2, maybe sometimes up to degree 3. But we are going to use it in the theory when we discuss, the main point where we'll use it is when we discuss that second derivative test, or the two-variable or multivariable version of the second derivative test for sorting minima and maxima. Okay, we're going to use this. This is going to be the key ingredient in doing that. Okay, so there's going to be some remainder which tends to 0 as we approach approach 0, 0, right? The remainder gets smaller and smaller as you get closer and closer to the point, and usually it gets smaller and smaller as you take higher order polynomials, and there's a full discussion of that in Calc 1, and things here are rather similar. Okay. Good. Questions about the Taylor polynomial? Is it clear? Good? Okay. So just remember that the way to remember what it is. Oh, one more thing I have to mention. If in general you're evaluating not around 0, 0, but around some point x0, y0, then all these 0, 0s are just going to be replaced by x0, y0, right? And everywhere where you see x, it's going to be x minus x0, and everywhere where you see y, it's going to be y minus y0. Clear? So in general, x0 and y0, and in general, x minus x0 and y minus y0. So throughout, I'm not going to write it all over the place. So that's how it shows up for a general point, and it's exactly the same idea of the proof. It's just much more easy to write it like this. Clear? Everybody good? Okay. So, great. So it's really much shorter than our discussion of the Taylor polynomial in Calculus 1, because there we kind of studied the theory and tried to really figure out all the phenomena and understand them and use it in various contexts. We used it to calculate limits and various things. And the same things are going to show up here, exactly the same things. So I'm not going to review the entire discussion just for two variable functions. Notice that I'm not even doing an example. You'll see in examples that it's easy. You just plug in the values, right? You have to find the derivatives, and then you can calculate the polynomial, the partial derivatives. Okay? I will use it when we get to discussing minima and maxima, and that's going to be in a few lectures from now. It's going to take a bit of time till we get there. Okay, so that's it for the Taylor polynomial.